Now let's start recording for Physics 2211 Lab 4 Oscillations. Our introduction here is our goals and our results. So our goals are to compare experimental tracker video data versus theoretical or closed grip modeling data for the observed motion of a mass attached to a spring. And the goal from this is with that observed data to plot the change in position versus change in time for each scenario, to observe a pattern for those graphs, and then plot the change in energy from the predicted scenario from both scripts, and using that plot find change in potential energy, kinetic, and total energy. Our results come out to be that our change in total energy is equal to 0, which is due to the law of conservation of energy, and is proven by our graphs, as what we discuss later. And both the experimental and theoretical modules create similar plots and are observed to be similar in nature. Then we also must go through our knowns and initial conditions. Our knowns are, our initial conditions are our system is just Earth, the mass, and the spring, which allows us to set our surrounding forces to 0, making the energy principle hold true, and since no external forces are acting upon it, our energy is equal to 0. Our spring constant of K is 6.83. The length of our spring pre-stretch, or L naught, is 0.123 meters. The mass of our ball is 0.402 kilograms, and our acceleration to gravity is 9.8 meters per second squared. Some physics concepts utilized here are net force equations, or F net equals delta P over delta T, the velocity update formula, Vf equals Vi plus F net over M times T, and the position update formula, Rf equals Ri plus V average times T delta T, with those latter two being used to calculate our change of position and velocity of our spring as it falls. Finally, we have the energy principle, which states that energy cannot be created nor destroyed, and the change in all the energy in the system is equal to the total work on the system. In this case, the system being closed, there is no external force, so our total energy is 0, because the only forces acting upon it are gravitational and spring, which are inside the equation. Here are the energy principle equations that are going to be used. Kinetic energy is equal to 1/2 m times Vf minus Vi squared. Gravitational potential energy is equal to m times g times h, or height. Our potential spring energy is 1/2 k times x squared, and our total energy is the sum of all three of those. Right here is our experimental data for our tracker video. And we can see how, as I press play here, we can follow the path of the object as it goes around the axis and as the spring oscillates back and forth. And from here, the following graphs are produced. We can see that in the x direction, it starts at below -1 and oscillates in cosinusoidal nature back to 0, up to -1, down, up, down, up, down, up. It's going back and forth between where it started and where it ended, almost like a pendulum. And for the y, because it's a spring, it's also oscillating up and down, up and down, up and down. And we see how it's oscillating right around -0.73 meters. So we can see how it's swinging both back and forth in pendulum nature and going up and down in spring nature, with those cycles occurring at relatively the same rate. So you go up to down is roughly 1.7-ish, and then down to up is once again roughly 1.7. We now have our theoretical data, or our glow script code. Up here in the top right corner, we can see how our initial mass is 0.402 kilograms. Our initial position is -0.116 in the x, -0.655 in the y, which is seen in the starting position on both of our graphs. And then going to here, we calculate see how the length of the spring changes over time. Below, we put in the energy equations from the previous slide, so we can calculate change in energy for our system. And we define these under the initialization that time is less than 9.5 seconds, or how long it took for the spring to move in the video. And then calculate our gravitational force in the system and the spring force in the system using the following equations of our gravitational is just m times g, and our spring is -k of the spring times s times L hat. Here's our goals for continued, and this is where we apply the momentum principle to find the update in the ball's velocity and update in the ball's position based on the equations from the previous slide. We then once again update the spring's length, and using that, calculate the change in energy using the energy equations from the previous slide, setting this to the initial energy and subtracting our change in energy from the initial one. Right here we have our experimental model, and we can see how it runs. So you see once I press start here, it follows a very similar path to that of our tracker video, just going back and forth between the two x positions and up and down between the two y's, forming that almost perfect circle. With that, we can see the graphs produced for it, and once again, we can see how for our theoretical models, our x starts right here at right around -0.1, goes up to right above 0.1, back down, up again, oscillating right around that 0.0 for x. And then for the y, we once again see how it is starting at right around -0.65, going down to -0.75-ish, and then right back up again, oscillating around that point, -0.70. So these are very, very similar in nature to the graphs produced from our experimental model, as they follow the exact same path and are having similar values match up. For energy, we can see how our total energy is this orange line right here, is equal to 0 the entire time, which is due to how our kinetic energy oscillates around the point as the y and the x values change and oscillate, and our delta U for our spring and gravitational potential energies are equal and opposite, meaning they offset, setting the energy equal to 0. What does this mean? For this lab, we see how the energy principle is satisfied. This is because how the change in total energy is equal to 0. The kinetic energy oscillates around the x-axis starting at 0, and the gravitational and spring potential energies are equal and opposite, setting everything to 0 and allowing for energy to cancel out and be conserved. We then estimate the average oscillation period. For this, we find our Gaussian graphs and see how long it takes to complete one cycle, and divide by how many complete cycles there are. For the x position, our average one was about 1.519 seconds, and for y, it was about 1.429 seconds. They are basically the same. The discrepancies are probably from how I may have misread the graph, as it was hard to complete the exact points, but it makes sense that it should take the exact amount of time to complete one cycle with the x and y directions for an oscillating spring pendulum. Thank you.